Okay, so I'm going to start just giving a brief overview of the development of gprMax. Talked yesterday in a bit more detail about how the code was created and then subsequently kind of rewritten and redeveloped later on, and the sort of structure and decisions in the design of the code. So just to recap that a little bit, the original version of gprMax was created by Antonis back in 1996, and it was actually written in C at that point. And over the sort of intervening years towards 2015, there was, a steady stream of small developments to the code, to that C code. One of the kind of maybe more important ones was the release of a version 2 of the software around about 2008. It was still C code at that point, but the main development there, or one of the main developments, was the ability to export geometry using the visualization toolkit format. And that basically meant that larger models with more detailed meshes could be more easily viewed in applications such as ParaView. So that was quite an important step forward. And I believe Antonis also did some work to the absorbing boundaries in the model in that time frame as well. But really, one of the biggest developments to the code happened in 2015 with the version 3 release, and that was the point at which we we rewrote everything from scratch using Python, and also using other toolboxes such as Cython and MPI to work on the performance and parallel parts of the code. And I'll talk about performance and parallelism a bit more tomorrow morning. We also decided at that point that probably one of the most important things that we needed a code name for our software. And I was working in Edinburgh at that point alongside Antonis, and we decided it would really only be appropriate to name our software after some very nice single malt Scottish whiskies. So the new version 3 in 2015 was named Bowmore. And then subsequently, with the next kind of point release in 2017, when we continued that theme. And the 2017 release was really focused around the creation of a GPU-based solver. And again, I'll talk more about that in detail tomorrow, but that was quite an important step in performance. Really a much bigger step in performance than using parallel CPU cores and threads using OpenMP. Moving to GPU was kind of at least an order of magnitude faster. So that was an important development, because as we'll see in various applications, performance can be really crucial, especially when you're having to run hundreds or thousands of forward models for things like full waveform inversion or machine learning. So that was a pretty important development. And then what we're going to be talking about mainly this morning is the upcoming version 4 release, which we're hoping to get out before the year end. So it's pretty much finalized at the moment, but we still have some issues to resolve, and we have some documentation to write. So there's still some steps to take before we can make that publicly available. And most importantly, John needs to decide, since it's a lot of his work, what whiskey he's going to choose to codename our release. So we await that information with bated breath. So what I want to kind of focus on this morning is discussing some of these features in the new release. But before I do that, I just wanted to point out that John has a lot of choice when it comes to choosing the name of this next release. You may not be aware, but there are hundreds of different malt whiskies in Scotland. So I'm sure he's going to be mulling over that decision for some time. Okay, so actually a lot of the changes that we've made in version 4 are what we might refer to as under the hood improvements. So not necessarily, you know, features that that you might see as a user, but lots of changes that we've made to both kind of improve the performance of the code further, but also restructure things in a way that will make future developments more straightforward, and also in a way that kind of improves the underlying structure of the code to make it a bit more accessible for other people to develop. So that's quite important to us because, as I said yesterday, at the moment, a lot of the actual changes directly to the code are being made by myself and also John and Antonis a little bit as well. So in some ways, you know, you can see that as a sort of bottleneck to code development, because Antonis and I are, you know, extremely busy with our kind of teaching and admin commitments at the universities that we work at. So we actually have, you know, quite limited time these days to develop the code, as much as we kind of enjoy doing that. So if we can kind of get the code structure and documentation to a point where other people can start to contribute developments to it, then that's really a promising future direction. So in terms of the kind of forward-facing features for the user in version 4, probably the most significant one is the ability to create subgridded meshes, and I'll explain, you know, in a bit more detail what that means shortly, and Antonis will kind of talk quite a lot further about subgridding after the coffee break. But subgridding also has quite a significant performance improvement as well, because instead of needing to run your entire mesh at the finest resolution for either the features that you want to model or to mitigate numerical dispersion, subgridding basically allows you to just have that fine mesh where you need it, and use a coarser mesh in the areas of the grid where you don't need that fine spatial resolution. So that obviously has an impact on improving the memory requirement for the grid, and in turn, therefore, the time that the simulation will take to complete. So one of the other things that we're doing is that we're going to release a library of several models of anti-personnel landmines. And these are models that Iraklis created as part of his PhD, and you can read about them in more detail in his thesis and in some of the subsequent papers that he's published. And he's also going to be giving a talk specifically on landmine modeling, I think tomorrow, in tomorrow's session. One of the other important things that we're doing that's aimed mostly for kind of advanced users and developers is that we have been working on a more fully featured application programming interface for gprMax. And that's really what I'm going to focus on showing you this morning, how you can use the API, how you use some more of the advanced features in gprMax, such as subgridding, such as customizable boundaries and such like, how you access those via this new API. And one other feature that we're kind of working on integrating at the moment, and it may or may not make the version 4 release. We don't have a clear decision on that yet, but we had a student working last summer on developing an OpenCL-based solver for gprMax. So that kind of sits alongside the CUDA-based GPU solver, and it allows gprMax to run on a wider variety of GPUs, and it also provides another parallel route to running on CPUs as well. So that work has largely been completed, but there's still a chunk to do in integrating that into the new code base. So that, as I say, it may or may not make version 4. So I wanted to talk a little bit about testing, because any changes that that we make to the code should always be checked against some sort of test suite. And often for Python-based codes, that means creating a test suite of what's called unit tests to test very small specific elements of the code to check that they're still performing as they should. So whilst at the moment we don't have a set of unit tests for gprMax, we do have a series of analytical and numerical comparisons that we have put together into a test suite. And generally when we make changes to the code, we run through this test suite to see that the responses from these various models are correct. So for example, the analytical comparison that we have is that we test gprMax against the analytical solution for a Hertzian dipole in free space, and I'll show you that in a moment. We also have a series of numerical comparisons which basically compare the current state of the code with a previously known good state of the code for different models. And again, one of those is the Hertzian dipole in free space. We also have one over a half space, one in a dispersive material, which is there principally to detect, to test the kind of dispersive material modeling tools in gprMax. So that's things like the multiple Debye model and the Lorenz and Drude modeling capabilities as well. And then we also test our magnetic dipole source as well. Another thing that we do, or that we have done, is that we have compared gprMax to another numerical method which is based on the method of moments. So we have a method of moments solution that calculates the impedance of a bow tie antenna. And if I remember, I think that method of moments came from MATLAB. So we have a comparison of the impedance of the bow tie calculated using FDTD in gprMax versus the method of moments calculation. And as I said, we don't have unit testing at the moment, but we want to move a little further in that direction, and certainly try and expand and improve our existing test suite and automate it a little bit more, especially because with gprMax being hosted on GitHub, there's a lot of tools that you can hook into that automatically run your code through a test suite whenever you make a change, so you don't have to kind of manually do that. So we have some plans for improvements in those areas, and I'll explain how we kind of may make those happen in a couple of slides time. So what I wanted to do was just kind of give you a brief demo of how one of the tests work, to show you what's going on. And I think, certainly for some people who are using gprMax for the first time, often what they quite like to do is to kind of test the code, if you like, by comparing it to to some sort of known solution, whether that be the analytical solution of a dipole in free space, or perhaps they might look at sort of me scattering from a sphere or something like that. So this is often a step that people like to look at when they begin considering gprMax for the first time. So I'm just going to switch over to Visual Studio Code, and I'm not going to go through this in any detail, but you'll basically find within the gprMax package there's a testing sub package, and within that there's a test models module, and that basically lists the different tests that are available, and by editing that module you can choose a specific test to run. So you can see here on line 53 there's a list of differently named tests. Some of these I've just talked about just now, and then a few lines further down you can see that I'm just selecting the first item of this list. So we're just going to test the current code against the solution, the analytical solution for a Hertzian dipole in free space. So we'll just run that just now. So this is now using version 4 of gprMax. So those that are familiar with the previous version might notice some small changes, which I'll talk about in a bit more detail as we go through the various other examples this morning. But one of the things that you will notice is that gprMax will now automatically detect any available GPU resources that you have, so that you can opt to use them to run your model if you want. So you can see here this these lines here basically describe my my machine, and also list I have a GeForce 1060 NVIDIA graphics card in it that's available to use. Anyway, so the model that we've run here is the numerical model of a Hertzian dipole in free space, and we have our script has basically compared that to the analytical solution and saved some plots. So if I just go to the directory where this happens, so I'm going to tests, basic models, and the analytical solution. So there's a couple of different PNG files in this folder. This is the main one here. So what you see again basically is the 6 electric and magnetic field components, the 3 electric components in the column on the left, and the magnetic components in the column on the right. And what's plotted in each of those basically is the analytical solution from theory, which is the sort of dotted green line, sort of, I guess it's termed the reference solution. And then the red line is the numerical model that we've just run with the new code. And you can see, looking at these graphs, they match nicely. What we can also do, though, is that the script will plot the specific differences between those 2 traces. So these are the same 6 field components. Now the y-axis is decibels. So you can see that the kind of largest difference here is in the HX and HY components. So we've got sort of minus 40 dB maximum difference occurring. And you can improve that difference actually further, because a lot of the difference here exists because of the precision that we're saving our output data. So by default, gprMax will use single precision to save the output. But if you want to work with more precision, then you can reinstall gprMax and change to double precision. And if you did that and run this test again, then those differences would become even smaller. So this is the kind of type of thing that we do as we're developing the code, to just check that the changes we're making aren't detrimental to the accuracy of the code. And as I say, we run several of these tests with different types of models to test the different aspects of the code. Okay, so on to kind of talking a bit more about some of these new features. So a couple of these features were developed initially through our participation in the Google Summer of Code program last year. And for those that don't know what that is, it's basically a funded international program from Google that allows students to be paid for 3 months to work on an open source project during their summer break. And any open source organization can be applied to be part of the Summer of Code program. And gprMax was one of only 200 organizations across the world that was selected last year to participate. And we were allocated funding for 2 students. So we could select 2 sort of projects that we wanted to work on and choose 2 students that applied to do that. So John was one of those students, and one of the projects that we wanted to work on was to bring basically the work that he'd already done on subgridding the finite difference time domain method and bring that into the public gprMax code. So as I said earlier, Antonis is going to talk in more detail about subgridding in his talk after the coffee break. So I'm not really going to talk too much now, but as I said before, subgridding can be really useful where you have really fine geometric details that you want to model. So that might be, for example, components in a GPR antenna, or it might be an area where you need fine spatial resolution to avoid numerical dispersion. So you might have materials in your model that have a high dielectric constant, such as water. And when you have that, you often need to use a small spatial resolution to avoid numerical dispersion. And obviously that becomes more significant if you also have a high frequency antenna that you have to use as well. That makes the spatial requirement even more demanding. And so being able to have a fine subgrid only in those specific areas of your mesh is a huge performance benefit, because you don't have to run your entire mesh at the smallest spatial resolution. So you improve the amount of memory that's required, and therefore the amount of time that the model will take to compute. Now, I'm going to talk about the API in a few slides' time, but one of the decisions we made with the API was that more advanced features like subgridding will only be accessible through the API. So at the moment, when you're specifying your model using hash commands, you can access all of the features that we have in gprMax, but that's going to change slightly with the API, and I'll explain that as we go. So just to show, you know, a couple of pictures, really, of subgridding at this point. And these kind of follow from the examples I've just talked about. So, you know, you might have a model that includes a fairly high frequency antenna, such as the GSSI 1.5 gigahertz. And to be able to model that, you need, you know, at least something as small as a 1 millimeter mesh. However, you may not need that resolution in the rest of your model. So you can basically use subgridding to retain a 1 millimeter mesh for the antenna, and with a subgridding ratio of 1 to 3, you might use a 3 millimeter mesh elsewhere in your model. So you can kind of see that in effect if we zoom in on a cross section of the antenna model. So what you see in the center of the picture there is the 1 millimeter mesh that's being used to model that antenna. And then out with that, we can use a 3 millimeter mesh for the rest of the grid. And this is a bit more of an extreme example. Here we're using a much higher subgridding ratio. So it's a 1 to 9 ratio. We're using a lower frequency antenna. So obviously, typically with a lower frequency antenna, you want your model domain to be much bigger because you're going to be exploring much deeper depths because of the lower frequency and better penetration. However, to model that 400 megahertz antenna, you still need a 1 millimeter grid because there's lots of detail inside the antenna that requires that spatial resolution. So it's models such as this where subgridding really starts to become beneficial. We can keep that 1 millimeter mesh for just the 400 megahertz antenna, and we can use 9 millimeters, for example, to simulate the rest of our subsurface. And in this case, you can also see that this model uses another one of the slightly more advanced features in gprMax, and that's the ability to create more realistic topographies or rough surfaces using fractal-based geometry. And again, here's a kind of a zoom in on the cross section of the antenna, where you can see the super fine resolution for the antenna, and then the grid kind of becomes much more coarse out with that. So the next thing I want to talk about is landmine modeling, and this is something that Iraklis will talk to you in detail about tomorrow. I'm just going to explain for the moment that we are going to be releasing some of these landmine models, and I'll show you in our documentation a little bit more about those. So as I said before, this is work that Iraklis did as part of his PhD thesis, and he's subsequently done further work since then. And these landmine models will be released in a similar way to our existing library of GPR antennas. So it will be as a user library sub-package, and that package contains 3 models of 3 different anti-personnel landmines. You can read some more of the details in the documentation, and you can relatively easily insert those into your models. So I'm just going to highlight a couple of lines of example code here. So actually, you only need one of them. It's even better. So to use any of those models in your own simulation, it's simply one line of code that's used to import the geometry and materials that describe the landmine and position them into your simulation. So at the bottom of the page here, this is just some pictures that show a couple of the different landmines and their corresponding meshes. And there's a lot of details in these models. Iraklis, created these models based on based on measuring the real mines themselves, and also deriving some of the material properties that exist within those. So as I say, those will be released with the new version later this year. So the sort of final part of what I want to talk about for the last half hour of this session is to kind of move on and focus on the new API that we are bringing. And before I get to that, I want to sort of explain what's currently available in gprMax to build models, and leading on from that, why we have decided to introduce a more fully featured API. So at the moment, you can create your input file using a series of simple hash commands. You can see some of those on the right-hand side of this slide. And you can do that by typing them into a text file, or you might automate that process using an external tool such as MATLAB. And the other kind of current way of doing slightly more complex things within the input file is the ability to run some Python code within the input file. So in effect, your input file or part of your input file can become like a kind of script, as it were. So again, in this example, you can see that we have these end Python blocks, and you can put whatever Python code you like within those blocks to automate parts of your input file, or in this case, to import from a library an existing antenna model. And within those blocks at the moment, we also provide some limited access to internal constants and variables. And the constants are mainly kind of common things that you might need to use, like the speed of light, permittivity of free space and such like. But they also give access to some variables that can be useful. For example, current model run. So that basically can be used if you have some geometry or parameter that you want to change every time you run your model. So an example of that might be you're trying to create a B-scan. Therefore, every time you run your model, you need to move your source or antenna. So you can see in the example here, where we're using this model of the GSSI antenna, we're using the variable current model run to change the X coordinate of the antenna. So essentially, every time we run an A-scan, our antenna structure is moved 5 millimeters in the X direction. So at the moment, there's some ability to do some Python scripting and sort of limited interaction with some under the hood variables. However, what we kind of begin to find is that as we introduce more advanced and complex features, the simple hash command starts to become a bit more cumbersome and full of a lot of different parameters and variables. So, in these examples, you can see we're creating a realistic soil model using a Poplinski-based model. And again, Iraklis is going to talk about these in much more detail later today. I'm just kind of showing how they're used at the moment. And, when in the previous example where we looked at surface topography, you can see using the add surface roughness command, they're starting to build a lot of parameters to be required to implement that. So one of the reasons for looking at an API is that it makes it a lot simpler in one sense to use these more complex and advanced features. And some of the more advanced features will only be accessible through the API going forward. So you see here, for example, that we're making some customizations to the PML boundaries in this PML CFS command. At the moment, you can do that by just specifying that hash command. In version 4 going forward, you'll only be able to do that using the API. And similarly, well, actually not similarly, but the new subgridding feature that's coming along will only be accessible through the API. So there'll be no hash command for using subgridding, because it's really something that is too complex and requires too many parameters to specify easily as a simple hash command. So that's the sort of the reasoning for creating the API. It's going to sit alongside the current ability to build models. So none of those things that I've talked about are going to go away. You're still going to be able, if you want to build things with hash commands, to build things, script hash commands using MATLAB, to use blocks of Python in your input file. All of those things will be retained, but you will also now have the choice of switching over to using our API. And that's really going to be both for people who want to access these new advanced features and also people who are just a bit more familiar with Python and software development and programming. And for those people, hopefully, it will offer a kind of new and an improved way of working. And finally, one of the other reasons for doing this is that there's starting to be more of a desire to combine gprMax with other packages. So you'll hear from Iraklis and Anya about how they're using gprMax within things like inversion and machine learning. And when you want to start doing that, and integrating gprMax and combining it with other software packages, then the best way of doing that is through an API. That means that gprMax can kind of continue to be developed and improved, and through the API it can communicate with other packages. So they will always benefit from gprMax being updated. They don't have something embedded within them that needs to be changed every time that we develop something new. Okay, so for the last kind of 20 minutes of this session, I'm just going to look at some specific example models in relation to the API to kind of show you what that looks like. And I'm going to begin with one of the simple models that we looked at yesterday. So if you were here yesterday, then you would have seen that we started off by creating a model of a two-dimensional model of a half space with a buried cylinder and a simple source. And the input file that we created, let me just find it. Here it is. It looked like this. So just a series of fairly straightforward and simple hash commands to construct what was a pretty simple model. Now, if we wanted to create exactly the same model using the new API, it's going to look a bit more like this. And for those of you who are familiar with Python, you know, a lot of this will be quite recognizable. For those of you who don't know Python, or who are not have no background in programming, this may look a little bit more daunting. And it may well be that initially, as you're developing your models, you decide to stick with using the hash commands. But I just want to talk through some of the features of the API and the way it works, and then we'll take a look at some more advanced examples of things that you can do. So the most important thing is happening here on line 3, which is importing the gprMax API into what is now a Python script. So you'll notice that the file extension of the model has changed from .in to .py. So this is now a fully fledged Python script. So we import gprMax, and then we start building up our model in the same way that we would normally do. So now, instead of using a hash command to specify the discretization, we import and use the discretization class. And actually the nice thing about the way this has been written, and also this particular tool that I'm using to show you the script, is that if you hover over the function, it will tell you, it will describe what that function is and what parameters you need to specify. So it explains that this function requires a parameter P1, which gives the spatial discretization in the X, Y, and Z directions. So that's quite useful. So we do similar things for the other kind of standard parts of our model to specify the time window, the size of the domain, and maybe to give our model some sort of title. And then we move down to creating any materials that we want. So you see that we create our half space material. And at this point, you hopefully begin to see the advantage of using the API. So, we can clearly see that we're defining a material here that has a relative permittivity of 6, a conductivity of 0, and magnetic properties as well. And those are described with variable names rather than just being standalone numbers in a hash command. So hopefully that aspect makes some of these parameters a bit more clear. And as I say, you can hover over the function that will give you further explanation of what's going on. So we then build our source and waveform and receiver in a similar way, and then we put our geometry in. So if you remember, it's a simple model. It has a box representing the half space, and it has a cylinder representing our meter cylinder. So that's all fairly similar to the way that we specify those in the input file with the hash commands. Now we kind of move to a slightly different functionality. So we've essentially created all those objects now, but with the API, what we need to do is we need to create a kind of modeling scene that all those objects will be added to. And that's what happens next. So we create a gprMax scene, which is essentially going to hold all of the objects in your model. And then after we've created the scene, we add all of those objects that we just defined above to that scene. We create a geometry view, which, if you remember, we also did in our input file. And then actually, what we're also doing down here is we're going to make some snapshots to view the field propagation in this model. So that becomes relatively straightforward to do with Python. We've got a simple for loop, and within that for loop, we're defining a snapshot. And I'm not going to go through this in all the detail, but basically a snapshot defines an area or volume of your model that you want to view. It defines a discretization to view it at, and it defines a time in the model simulation that you want to take that snapshot. So we're essentially taking a series of 30 snapshots over the duration of the model that are going to allow us to view the propagation. And then we actually run our model, so we can run our model now from within this script. We don't have to call it separately like we did yesterday from the command line. When we run this script, our model is just going to automatically run. And then at the bottom here, I've added some plotting. So this is going to automatically plot the output of our model immediately after it's finished running, which can be quite useful. So I'm just going to show you, I'm going to execute that script now and show you what it looks like. So we just run it as you would run any Python script. You'll notice, we're not specifying gprMax. We're just giving the name of the script that we want to run. And it runs pretty quickly because it's quite a small model, and it plots the A scan of our output. So let me just close that plot down, and we'll go back and have a look at the output that's been generated. So this is pretty similar to what we looked at yesterday. You see basically a list of all the objects that we created as part of our model. Those are all the snapshot objects that we specified in our for loop. And most of this looks familiar to what we saw yesterday. You'll see as the simulation was executing, or rather after the simulation had finished executing, gprMax then wrote all of our snapshot files out. So we viewed the output from the receiver, which was that A scan that we saw, and we can now go and look at our snapshots in ParaView. So I'm going to do this quite quickly because I'm kind of rapidly running out of time. So what I'm going to do first of all is load in the geometry mesh, so we can see that. And this is, we did this yesterday, so that's just the same thing we did yesterday. And now I'm going to open up in this folder here the snapshots of the field that we've just created. I'm going to load them in. Now let me just move this down. So you'll see that we now have the ability to view the electric or magnetic fields in our snapshots. So if I just turn on the electric field just now and view that as a surface, you can see now that we have an image of the initial field, and you can see that the first snapshot was taken just after the source began to fire, and then we can step through that snapshot and look to see how that field propagates within the model. What you might need to do in ParaView is rescale some of the colors used to visualize the field. I'm not going to do that now, but if you do that, then you can see some more detail within the field. So at the moment this looks quite saturated, so you might want to change the scaling so we can see some more detail in the field. But hopefully you get an idea from that of what's going on. So I'm going to move on quite quickly now to some more complex models. So this next example now is looking at modeling an antenna model in free space using the new API. So the start of this script looks fairly similar to the one we just looked at. We're defining things like the domain and the discretization and the time window, and we're adding all of those to our modeling scene. And then slightly further down here is where we go and import our GSSI model. So this antenna like GSSI 1500 function basically is what's used to import our model. And again, if you hover over that, it explains what the function is and the parameters that you need to specify. So the main thing is basically the coordinates of where you want to put the antenna in your model. And once you've done that, you then add those antenna objects to your scene. So in a similar way that we added the domain and the discretization to our scene, we have to add all of the objects in our antenna to the scene. And this is where it can become quite useful, because, for example, if you wanted to rotate that antenna into another orientation, you can quite easily do that as you're adding the objects to the scene. So you'll see this line here that's commented out. If I wanted to rotate my antenna through 90 degrees, then if I uncomment this line, then that will quite simply and easily do that as it's being added. So that's kind of one of the powerful things about having an API, is that you can start doing things like that fairly easily. And then down the bottom here, we have a couple of different geometry views to visualize that. And then at the bottom, our statement to run the model. And just to mention, you'll see, there are some parameters that are specified as you give the command to run the model. And most of the parameters here represent the same flags that you would have used if you were running this model directly at the command line. So for example, if you just wanted to create the mesh and not run the simulation, then I could switch this geometry only flag to true, and it would do that. Similarly, you can see that I have a GPU flag that's set to a number here, and that basically tells gprMax I want to run this model on my GPU. If you don't have a GPU or you don't want to do that, then you can just set that flag to none. So you can quite easily do that. So the next example I'm going to look at is starting to take advantage of some of these more complex features that we've previously mentioned. So this is a model that uses a Poplinski soil representation, and it uses a fractal box to distribute those soil properties in a fractal way throughout a volume in the model. So this is hopefully where the power of the API starts to kind of become apparent, because when we're specifying things like the Poplinski soil, which has quite a few different parameters, it becomes kind of a lot more clear what each parameter is. So you can see, we're specifying things like the sand fraction and the clay fraction of the soil, and lower and upper bounds for water content, and we can directly see what those parameters are. We don't have to kind of refer back to the documentation to look up the number from the hash command. Similarly with the fractal box, it's quite parameter heavy, but they're well described via the API. And I'm going to continue moving on rather than running these examples, because we've only got a few minutes left. I want to show you two more examples before we finish. One of those is a model that uses the landmines that we've just talked about. So again, the kind of initial part it should be getting fairly familiar now. We're specifying the things like the domain and the discretization. And then as we move down, we can start adding some more of these more complex features. So again, we're using a Poplinski soil model. We're creating a fractal box to distribute those properties. We're now adding a rough surface to that fractal box to maybe represent some realistic topography. We're also adding surface water, so you might have a scenario where you have pools of water on the surface of your model. You can see that we can add those quite simply through the API, and we can even add grass to our model by issuing a command to do that. And once we've kind of set up all of this fairly complex background, we can then add things like our antenna model that we've already discussed. And after that, we can start to add more complex targets. So here I'm importing a model of a PMA landmine and using that within that complex subsurface that we've created. So this Python script that uses the API is basically creating what is a really quite complex subsurface model that also includes detailed models of a transducer and also detailed models of a target, which in this case was the landmine. So the final example I want to look at this morning uses the subgridding functionality that we've touched on briefly. And this is really where the use of the API starts to become a little bit more complex and involved. And this is the area that we're actually putting quite a lot of effort into writing documentation for at the moment. So I'm just going to describe some of the parts of this script that we're going to look at. And essentially the beginning of it here is the same as the other scripts that we've looked at that don't use subgridding. You're defining the kind of basic parameters and adding them to a general scene. And that general scene is basically your main mesh, or the kind of the coarse mesh in this model. So you see again, in this case, we're creating some sort of half space material, and that's getting added to the main scene. Similarly, we're creating a box with that half space material and adding that object to our main scene. And then as we kind of move down, we start adding, continue adding more objects to our main scene. So this model also has a buried metal pipe in it, and we add that to our main scene. But now what we're going to do, because this model, I probably should have said that at the start, this is a model of an antenna over a half space with a metal pipe. And what we're interested in doing here is using a subgrid to model our antenna with a lot of detail, and then using a coarser mesh for the rest of the geometry. So you'll see towards the middle of this script that we start defining things like our subgrid ratio, and then at this point we actually create a subgrid object, and we specify the extent of that object and the subgridding ratio that we've just defined that we want to use, and we add that object to our main scene. And then after that, we start importing our antenna, which is what's happening here. But the difference now is that instead of adding those antenna objects to our main scene, we're adding those antenna objects to that subgrid that we just created. So in that respect, once you kind of understand how the API works, it's relatively easy then to create different subgrids and to add objects to different subgrids. And then the latter part of this script, is very similar to what we've seen before. So we're creating geometry views that are going to allow us to view our mesh, and we're creating a series of snapshots that are going to allow us to view the way the fields are propagating in this model. And the thing to be aware of, though, is that when you then go to run your model, you need to tell gprMax that model contains subgrids. So you simply set the subgridding flag to true, and then gprMax will process and run this model, being aware that there are subgridded meshes within it. So that kind of brings me to the end of the examples that I wanted to show. and also brings me to the end of this morning's session. So it's been a bit of a sort of whistle-stop tour of lots of different features, some of which exist already, some of which are coming in version 4. And, you know, as we go through some of the other presentations, some of the kind of theory behind some of these features and more detail on the way they work will become apparent. So thank you for listening.